Now in this video we're going to generate a summary note on all the gas laws and combining different gas laws to get an ideal gas law, and also various strategies on how to solve problems related to gases, mainly at the little bit of early undergrad / high school grade 11 level. So in here we're going to start off with Boyle's law, who was actually the one that brought up the relationship between the pressure and that of volume. And what he noticed is that if you increase the pressure, you actually get a result in the volume, which is a decrease. So as a result, he noticed that there is an inverse relationship with those two variables, and when you integrate the constant, which is KB, we actually have a formula that we frequently use, which is as follows: P1 multiplied by V1 equals to P2 multiplied by V2. So in this case, if you're given three variables and you're able to know what they are, you can actually determine the unknown variable based on any question that is given. Now, looking at the plot of the Boyle's law relationship between pressure and volume, what he said was that, hey, once you create a plot line showing this relationship, we actually get a specific hyperbola right here, which shows an inverse variation. And then if you pick one of the variables and do 1 over that variable and plot it with the other variable right there, we actually move away from the hyperbola to a more linear plot right there, which is showing the inverse relationship between both variables. So now that's out of the way, we're going to move into another scientist who is called Gay-Lussac, who showed the relationship between the pressure and that of temperature. And he said that if you increase the pressure, you actually cause an increase in temperature. So as a result, the constant is actually shown on each plot line to be the same with pressure with that of temperature. And in this case, once we're able to accomplish that, there is a frequent formula that is used where we have P1 over T1 equals to P2 over T2. So if you create a line graph, we actually have a couple of points right there, and then when you extrapolate all the way down, you actually hit a point here, which is actually the point where we have zero pressure. That means particles are not moving. That particular temperature is known to be the absolute zero. And at this point here, we actually were able to generate the Kelvin scale, and that is where you must be able to use that Kelvins as your unit for temperature. So if you're given a value in degrees Celsius, you add the value to this number 273, and this will give you your Kelvin value. So now that's out of the way, we're going to move over to another scientist, also a French scientist, Charles, who showed the relationship between the volume and that of the temperature. And what he noticed is that if you increase the volume, you automatically increase the temperature, which shows that this is a direct relationship where Kc is actually the constant at every single point, which is really dependent on the conditions. The conditions must be constant in there. So for that particular case, we actually have with temperature, and a frequent formula is P1 over T1 equals to V2 over T2. So in this particular case, if you draw a graph, you're actually able to get a linear plot right there, and by that way this shows the relationship between the volume and temperature. This one here, just to be consistent with the labeling of the axis on the Gay-Lussac scale, we actually have that with pressure. Now combining all these three laws together actually result in the combined gas law, which is as follows: P1 multiplied by V1 over T1 equals to P2 times V2 over T2. In this case, you are able to fulfill all three laws into one particular law, where there is an inverse relationship between pressure and volume, and there is a direct relationship with pressure and temperature and volume and temperature, and then you can actually determine an unknown based on 5 known variables that are given in any question. So take note that temperature must be in Kelvin. Convert to Kelvin first before solving the problem, and sometimes you need to be aware of what the units are. Mainly for pressure and volume, they must be in the same unit. Most times you might be given the pressure in kilopascals and the volume will be given mainly in liters. So now that's out of the way for the combined gas law, we're going to dive into the Avogadro's law, which shows the relationship between the volume and the number of moles, which is represented as N, which shows a direct relationship. It's like blowing a balloon. If you add more particles, that increases the volume of that balloon at conditions that are constant, like constant pressure, constant temperature. Once we're able to do that, we get our constant, which is K, I will say A, with respect to the number of moles, and then a frequent formula you will see is V1 over N1 equals to V2 over N2, and as a result, once you're able to generate that and incorporate it into our combined gas law, we actually generate our molar combined gas law, where we incorporate our N as a new variable into the P1 V1 over T1. So we have our number of moles right there, and then if you want to find any unknown, you will be given 7 knowns and you'll be asked to determine an unknown, V2 over N2 T2 right there. And in this case, N is considered to be the number of moles. So based on the molar combined gas law, we will actually subject one of these variables to STP conditions, and that is actually important to generate a specific condition where we can actually, instead of putting at standard temperature and pressure conditions variables, we can just use a specific constant. So in this case, where we actually make our pressure 1 to be 101.3 kilopascals, and then T1 to be at 273 kelvins. This is usually the freezing point of water. And then at sea level, we actually have the standard molar volume to be N1 to be equals to 1 mole, which is equivalent to the volume of 22.4 liters. So once we plug that into this particular formula right here, we actually generate our ideal gas law, which is as follows: PV equals nRT. So in this case, our nRR is actually equals to 8.31 and some other significant figures right there. But take note of the unit, which is kilopascal times liter over moles times kelvins. So once you're able to recognize these, you can be able to solve any question that has the pressure, the volume, and temperature, and you have to determine the number of moles. From the number of moles, you can actually get the mass of a particular compound when specified by using the molar mass, which is big M. And if you want to get back to number of moles, you're also using the molar mass of that particular compound that is given. Sometimes you might be given a reaction where you actually have a particular compound right here, and it is subjected to water, and what is released as a process is this particular gas, and we actually have this particular base right there. So the cool thing about this reaction is that we have a solid here, we have a liquid here, we have a gas released, and this is an aqueous solution. So if you're given the mass of that, you can actually find the volume of gas released in here. If you're given the volume, you can actually find the mass that is actually required right here. So it all goes back and forth in terms of the number of moles, and also balanced equation, which is merely a 1-to-1 ratio based on this particular reactant and this particular product right there. So that is about it for this particular video. Hope you're able to understand this. Please hit the comment down below. Let me hear your thought about the ideal gas law, combined laws right here, and how to use them, strategies on how to approach various questions, and also any questions that you might have. All the same, stay smart and believe in yourselves.